So welcome everybody to our flatband physics of flatband conference. Today we have the pleasure to host the IBS Physics Colloquium inside the conference. So let me remind for those who don't know what the Physics Colloquium is. So the IBS Physics Colloquium is a joint activity which includes all the IBS physics centers in the Dijon area. However, in the pandemic time, we somehow decided to extend this activity to include also the other IBS centers, which are outside of Dijon. Today our colloquium will be, let's say, the speaker of our colloquium will be Daniel Leykam from National University of Singapore. So let me introduce our speaker. So Daniel got his PhD in 2015 in the Australian National University with a thesis whose title was Wave and Spectral Singularities in Photonic Lattices. And he also got a prize for that, the Australian Institute of Physics Bragg Gold Medal. After that, he moved as a postdoctoral fellow in Nanyang Technological University in Singapore up to 2017. And then he got the YSF fellow in IBS, and he moved to IBS, and he became a team leader here for, let's say, 3 years, I would say. And actually, if I understand correctly, now I'm sitting in what was his office before leaving, if I understand correctly. During the time, he was also an assistant professor in UST, the University of Science and Technology, again in Dijon, and starting from August 2020, he is a senior research fellow in the National University of Singapore. Now, his research interests, as far as I understand, cover, for example, photonic and, of course, flatbands. This is the reason why he is the colloquium speaker today. And but before starting the colloquium, whose title is pretty interesting, Flatbands and Sharp Physics, I want to ask our director, Sergei Fleck, to say a few words more about the speaker, I guess. So please, Sergei.
Yeah, thanks, Dario, and welcome, Daniel. I just wanted to add on a more personal note that the reason why we are all here at this colloquium, but also at this conference, is actually Daniel. You could say at least so. I hope Daniel forgives me that I make him that much important in the history of science. But it really happened that way. I just moved out of Dresden to Auckland, New Zealand, and then went over the ditch to pay a visit to the Nonlinear Physics Center of Yuri Kivshar. And that's where I met Daniel, who together with Anton Desyatnikov asked me whether I can be of some, whether I want to participate and be of some help maybe in some project they were working on, which was nonlinear flatbands. And by that time, I didn't know anything about flatbands. So that's how I got interested in flatbands. And so thanks, Daniel, for sharing these news with me at that time in 2013 or whenever that was. And it's a great pleasure to have you back here with us as a colloquium speaker. And thanks, Dario, for these few minutes which you gave me. I'm muting myself.
Okay, so after this additional news that I didn't know, I think it's time to start our colloquium. So Daniel, please, you can start.
Okay, thank you for the kind introduction. And thanks to the organizers for giving me the opportunity to not only speak at this workshop, but to give a colloquium talk. I was quite surprised because even though I've been working on this topic for 8 years now, I only ever presented this topic on 2 different occasions. So I'm not very experienced at giving talks on flatband physics. And of course, it'd be much nicer to give this talk in person, but we can't really do much at the moment. So I'm going to be, since this is a colloquium talk rather than a workshop talk, my aim is to give a broad, accessible introduction to flatband physics, focusing on how I got interested in this exciting field. And then if time permits, I will also cover some more recent developments, focusing on experimental studies of flatbands and some possible interesting future research directions. So to give some background, you already heard, so my primary research area is photonics. I'm also working a bit now more on quantum stuff. And so the broad background for this work is to understand wave propagation in complex lattices. So for our purposes, we can consider either quantum particles or classical light beams governed by Schrödinger-like wave equations, as you see here. And we consider wave propagation in the presence of a potential that is periodic in space. And as we all know, using Bloch's theorem, we know that the modes of this system can take the form of Bloch waves, which have this spatial periodicity. And the energy eigenvalues E form a discrete set of bands, which depend continuously on the momentum K of your eigenstate. This gives rise to these energy band structures, which reveal a lot of information about the wave transport properties in your medium. For example, the derivative or the slope of the energy bands with respect to the momentum will give you the local wave group velocity at that wave vector and energy. So back in 2012, when I first started working on my PhD studies, the topic of wave transport in Dirac materials was a topic of growing interest. So Dirac materials include graphene and other 2D materials, and these systems exhibit band crossing points or intersections of their energy bands. These band crossing points are particularly interesting because waves propagating in the vicinity of these conical intersections can mimic various interesting relativistic effects. So for example, in graphene, close to these band crossing points, which are known as Dirac points, the electronic properties are governed by an effective Dirac equation in 2 dimensions. So this means that by studying these systems which have band crossings, you can do tabletop emulation of various relativistic wave effects using low energy particles. These band crossing points can occur either due to some symmetry protection, as is the case in graphene, or they can also be generated by fine-tuning your lattice parameters. So in this context, I was interested in trying to figure out how to observe these kinds of relativistic wave effects using photonic systems, photonic lattices, photonic crystals. So we were particularly interested in whether it's possible to realize conical dispersion relations beyond those seen in graphene. And this led us to considering this particular lattice, which is shown here on the left, which is the face-centered square lattice, which is now more commonly known as the Lieb lattice. And the name derives from Elliott Lieb, who first studied this lattice model in 1989 as a simple model for ferrimagnetism. So for the waves propagating this Lieb lattice, the type binding approximation have the following band structure, which you see in the middle plot here. So this lattice has 3 sublattice, 3 type binding bands. The upper and lower bands have, well, you see that the middle band is perfectly flat.
Do we have some problem, right?
Yeah, we have a problem. Daniel, we don't, you're frozen, you seem to be.
Yes.
Daniel, if you hear us, maybe you want to disconnect and come back.
Yes.
If that helps. Okay.
So it looks.
He did something.
Hear us? Yes.
And we are still live on YouTube. Oh my God. So now we have to wait until they fix this
yes.
ocean cable between Singapore and the rest of the world.
Maybe you can send him an email. Maybe he doesn't know that he's not connected.
Well, he probably knows that.
Because because he disconnected, right?
Disconnected, right? The question is only whether he will be able to reconnect again during a reasonable time. Otherwise, we'll have to. Oh, here we go. Okay, Daniel is back. We don't hear you, Daniel. You want to maybe?
Oh, hi. Yeah, sorry, the Wi-Fi dropped out, so I'm just waiting to see whether it reconnects.
Mm-hmm.
Oh.
No, that's not good.
Daniel,
you're frozen again. You're semi-frozen again, so somehow your connection is very weak. You maybe want to switch off your video, and if that helps.
Hello.
Yeah, we hear you. Yes. But you are from time to time frozen for short periods. Okay.
Oh.
We see your screen.
Okay. Sorry about that.
Right.
So where was I? So we have this conical intersection of the bands, which resembles that of graphene, but in addition we have this central band, which has wave energy independent of the momentum, and this forms a flat band. So this is interesting because in the flat band, the wave grip velocity vanishes, which means you can have perfect wave localization just due to interference rather than any confining potential. So it was known in the case of graphene that this conical dispersion relation leads to a peculiar conical diffraction if you take a wave packet and let it evolve in time. And we were originally interested in how this conical diffraction will behave in the context of this generalized conical dispersion relation. So conical diffraction, you start with a beam shape which is initially Gaussian, and it expands as it evolves into this ring shape due to the fact that all waves in these conical bands propagate at the same speed. This paper was quite special for me because this was my first paper to be rejected from physical review letters. And the referee commented that this was an interesting effect, but probably experimental defections and disorder will make this effect extremely challenging to observe in experiments. So after we published this paper, we started looking into the question of how disorder might affect this conical dispersion relation and conical diffraction. And we spent several months looking at this without making much progress.
Sorry, Daniel, can I ask a question? I mean, yes. The paper that you showed before somehow was the first time that this, let's say, flat bands phenomenon was observed? No, right? I mean, the idea of having...
Yes, so if you maybe, so on this previous slide, so I forgot to mention that there were several existing works from 2010 looking at this lattice in the context of cold atoms for optical lattices for cold atoms and other studies in solid state physics. At least as far as I'm aware, ours was the first study to look at this in the context of photonic systems.
I see. Okay, thanks.
Yeah, so we wanted to see how disorder might affect this this effect. So just to remind non-specialists, disorder can have quite a profound effect on wave propagation in lattices because it can lead to this phenomenon of Anderson localization, which was first predicted in the 1950s. So if you have disorder in 1- and 2-dimensional lattices, no matter how weak, you end up with a complete suppression of wave transport. All the eigenmodes become localized by any non-zero disorder. This can already be captured by very simple type binding models of the form which is shown here, where you have a 1-dimensional lattice with hopping between neighboring sites, and each site has a random potential drawn uniformly from some interval.
Yeah, but in 1 dimension, you have always localization in this mode.
Yes. Yeah, so it's on the other hand, in 3D, you get a transition from extended to localized modes at a critical disorder strength.
Okay.
Yeah, so we did some numerical simulations, and indeed, as you increase the strength of the disorder, eventually this nice conical diffraction pattern gets washed out, and you see this wave localization. However, the onset of this localization occurred at quite strong disorder strengths, which made any analytical description or analytical explanation beyond our capabilities. And so we were unsure how to proceed further on this topic. We did prepare a rough paper draft, which you see here, but we never published these numerical results. Then we got lucky because that month, so in end of February 2013, we had a visitor, Sergei Floquet, come to ANU to give a seminar. And so for those of you who don't know, Sergei Floquet is a big expert on wave transport in disordered lattices and nonlinear lattices, which was precisely the problem we were trying to solve. And so we had the opportunity to have a discussion with him. I don't remember whether it was before or after his seminar, but we showed him these preliminary results. And he provided 3 very valuable suggestions. So first of all, he recommended studying a much simpler problem. So rather than looking at Anderson localization in the 2-dimensional Lie lattice, perhaps it'd be possible to study a simpler 1-dimensional lattice. And so this led us to considering this 1-dimensional diamond lattice, which is shown here. And the band structure you see in the middle here is very similar in that it has 3 bands, 2 of them are dispersive, and we have this middle flat band sandwiched in between. Second, he said that it'd be better to study the spectral properties of this system rather than the dynamical properties. So that means rather than looking at the propagation of wave packets in the presence of disorder, we should simply study the properties of the eigenstates of the disordered system. Importantly, by looking at the spectral properties, you can obtain quantities which are energy resolved, allowing you just to distinguish the flat band from the dispersive bands. And finally, he said it might be more interesting to focus on the role played by the flat band and how it is affected by the disorder, rather than considering the conical diffraction occurring in the dispersive bands, which we found was rather weakly affected by the disorder. So after our meeting in the morning, I spent the rest of the day coding this eigenstate calculation and computing properties of the eigenstates. And the next morning, I think I showed him the plots on the right. So here we're plotting the localization length of the eigenstates as a function of energy for different strengths of the disorder, which is shown in the different colors. And so what you see here is for the weak disorder, so the blue and red curves, we see this pronounced dip in the localization length. in the vicinity of the flat band at 0 energy. And so this indicates that the flat band is much more strongly affected by the disorder and much more strongly localized compared to the modes belonging to the other bands. Moreover, the shape of this dip, its width and its contrast, it changes with the disorder strength. And this indicates this is suggestive of different scaling properties of the modes at 0 and non-zero energies. So indeed, if you calculate the localization length of your eigenstates as a function of the disorder strength W, we obtain we obtain different power law behaviors, which are shown in this plot. So this is a log-log plot, disorder strength on the bottom, localization length on the vertical axis. And here the different straight lines indicate power laws with different exponents. So what we firstly see here is if we plot the behavior of the localization length that's away from the flat band energy, for example, this blue curve here, in one of the dispersive bands, we obtain a scaling exponent of nu equal to 2, which is the well-known scaling of the conventional Anderson model. So the dispersive bands behave very similar to conventional one-dimensional lattices. On the other hand, if we look at the scaling of the modes at the flat band at energy 0, which is this red curve here, what you see is the scaling with disorder strength is much weaker. The exponent turns out to be approximately 1.3, I think 1.33, maybe even 4/3. So this indicates qualitatively different behavior compared to the regular Anderson model. Now, we tried to explain this scaling by attempting to reduce the eigenvalue problem for the diamond chain to a more conventional Anderson model of localization. This can be done by eliminating some of the site amplitudes from your eigenvalue problem, like so, leaving you with an eigenvalue problem for just a single regular one-dimensional lattice, in this case the B sites. But this eigenvalue problem becomes a bit different from the conventional Anderson model in that the disorder and the coupling strengths, they both have disorder. This disorder is correlated and it's also energy dependent. So we left this peculiar scaling with disorder strength as a mystery to be solved in future work. And we published our results in PRB. And Sergey invited me to visit him in Auckland later that year to continue working on this topic. So in Auckland, we tried to get to the bottom of this peculiar scaling. We looked at the properties of various other disordered flat band lattices. So here we have a variety of 1D lattices which are sketched with different energy band structures exhibiting flat bands. We also performed a lot of numerical simulations, recovering a variety of different scaling exponents, which we attempted to explain. These figures eventually were polished and became part of a follow-up paper. So after staring at these puzzling numerical results for some time, Sergey had the insight that this might be something, this could be related to the Fano resonance phenomenon. So Fano resonance refers to an interaction between a single bound mode and a continuum of delocalized modes, which gives rise to a strongly asymmetric and distinct scattering spectrum known as a Fano resonance, which is well known and widely used in photonics. So in the case of flat band lattices, the strongly localized flat band mode can be taken to be the bound state, and the dispersive states, which are weakly localized, can form a continuum. And then we hoped to explain this unconventional scaling in terms of a self-consistent interaction between these strongly bound and weakly bound modes. And so in particular, disorder induces scattering and some interaction between this discrete state and the continuum. So using this intuition, we found that by first eliminating the flat band modes from this disordered eigenvalue problem, we could obtain a regular Anderson model on a simple one-dimensional lattice with a relatively simple disordered potential, which is shown here. So here we have this effective Anderson eigenvalue problem. So Pn is our mode amplitude at the nth side. The two terms on the right correspond to hopping between the neighboring sides. And then this middle term in the big brackets corresponds to our effective disorder potential, which involves two parts. The first part is a symmetric part of the disorder distribution, which gives you a bounded disorder potential. The second term describes the disorder-induced coupling between the flat band mode and the delocalized dispersive band modes. And this coupling involves an energy term on the denominator. So this is a resonant coupling term. And in fact, this resonant coupling gives rise to a resonant enhancement of the effective disorder strength close to the energy of the flat. Potential is no longer bounded, but it exhibits fat or heavy tails, obeying a Lorentz distribution. So it turns out the Anderson model with Lorentz distributed disorder was solved way back in the 1970s by Thales and Ishii in separate papers. And they showed that you can obtain the spectral properties, all the spectral properties exactly. So by simply mapping the flat band eigenvalue problem onto this Cauchy or Lorentz distributed disorder problem, which was solved previously, we were able to finally explain the peculiar scaling of the flat band localization length. So in particular, when the flat band is spectrally isolated from other dispersive bands by a gap, you don't have any resonant interaction between the flat and dispersive band modes. And then in this case, the mode localization is dictated purely by the localization of the flat band modes. And this is independent of the disorder strength. This corresponds to scaling with an exponent 0, which is shown on the highlighted points from the numerics in the bottom here. When the flat band is embedded or touching a dispersive band, you get a resonant interaction between the two different types of modes, which lead to different scalings of the localization length with the disorder strength. In particular, for a flat band located precisely at the edge of a dispersive band, the predicted exponent is equal to 1/2, which is highlighted here. For a flat band embedded within the dispersive band, you get an exponent of 1. In both cases, these scaling laws lead to much stronger localization compared to the conventional Anderson model scaling, which is but in all these cases, we get very nice agreement between the analytical prediction and the numerical results.
I think we lost him again, right?
Yes, I'm not seeing anything more.
Daniel, we lost you.
Okay. Yeah.
Probably hears us. Rudolf.
Who put that?
Rudolf. Oh, here's Daniel again. We don't hear you.
Yeah.
Can you just, please?
Yeah, sorry, I'm going off my phone now because the Wi-Fi is so unstable, it seems.
Let's hope your phone is charged.
Yeah, so, yeah, so we can get these nice and beautiful analytical expressions for the density of states and localization length in the presence of correlated disorder. So to summarize what we found from the early studies is that firstly, the huge degeneracy of the flat bands leads to a very sharp sensitivity to perturbations. Usually when you have such large degeneracies, perturbation approaches can typically fail. Flat band systems are, however, quite remarkable in that there are various tricks we can perform, such as basis transformations, which allow us to eliminate the flat band and resulting in simple models with resonantly enhanced perturbations that can be solved either exactly or semi-analytically. And so this makes these flat band systems quite a valuable setting for understanding various strongly interacting phenomena. So now I have about 15 minutes left, I think. So now I'm going to talk a bit about some more recent developments in this field. I noticed that most of the talks at the workshop are given by theorists, so I'm going to cover some experimental developments from the past few years. So we already heard from some of the other speakers at this workshop that flat bands have quite a long history. And they were first studied more than 30 years ago. However, what flat band lattices have in common is that they typically have quite complicated lattice structures. For example, with coupling only to certain neighbors, or with non-close packed lattice structures, or with fine-tuned second neighbor or even more distant neighbor couplings. So these kinds of lattices are not commonly found in natural materials. And therefore, to observe flat band effects in experiments, it's usually necessary to artificially create these lattices. So the first implementation of a flat band lattice, to my knowledge, came in 1999. This was based on a superconducting wire network, which was used to implement the dice lattice, which is a two-dimensional flat band lattice. Now, the peculiar feature of the dice lattice is that if you fine-tune an applied magnetic field, you can make all of the energy bands perfectly flat, which means that all waves are localized regardless of their energy. So this lattice was fabricated using electron beam lithography, using superconducting wires. And in this first experiment, they observed indirectly a signature of this flat spectrum, which was the presence of a broadened superconducting transition as a function of the magnetic field strength or magnetic flux quanta. This broadened transition at half a flux quantum was attributed to the flat band leading to localization of your superconducting state and it forming many different incoherent domains. And so each domain is affected by the local disorder, and therefore its superconducting transition temperature is shifted with respect to other local states. And so this study highlights one of the main challenges with observing flat band effects in experiments. That is the need for high quality fabrication in order to minimize the influence of disorder. Because if the disorder is too strong, the interesting signatures of the flat band will just be completely washed out. So renewed interest in experimental flat bands picked up from 2013, thanks to advances in fabrication techniques. For example, the Dirac laser writing technique. Hang on. So for example, the direct laser writing technique allows you to perform tailored fabrication of two-dimensional type binding lattices for optical waveguide arrays. And I think we'll hear more about this in the next talk. Another front has been, or another breakthrough has been the ability to create high-quality optical lattices for cold atoms. Improvements over the past decade have allowed for the implementation of the two-dimensional lead lattice as a trap for cold atoms. And some signatures of the flat band were observed. More recently, experimentalists have been able to use internal atomic degrees of freedom as a way of implementing more complex quasi-one-dimensional lattices, including this two-leg lattice structure, which with a tunable magnetic flux, which can exhibit a dispersion relation approaching, but not quite that of a flat band. So the main challenge with the cold atom platform is that you have a trade-off in that you ideally want the lattice to be deep enough so that the type binding approximation is good and you get a sufficiently flat band. But on the other hand, if the lattice is too deep, you won't see any appreciable coupling between your neighboring sites, and you won't be able to observe any of the interesting effects caused by the flat band. Now, the most remarkable breakthrough, in my opinion, has been the creation of engineered flat band lattices at the atomic scale. So in these experiments, what they do is that they use a scanning tunneling microscope to add or remove individual atoms from a monolayer, which is shown on the left here. So here they have a monolayer of copper atoms, and a lead lattice can be created by creating vacancies in this monolayer, which is shown in black here. Then using the same microscope, you can perform energy-resolved measurements of the electronic density in order to map out the eigenmodes of the dispersive band and the flat bands. And so just last year, this same technique has been used to realize a variety of quasi-one-dimensional flat band lattices. The main limitation of this platform is that interaction effects seem to be rather weak, which means you can't really look at many body phenomena that easily. So finally, in the last 5 minutes, I'll finish with some directions which I think are interesting for future research. So the superconducting wire platform, which I mentioned previously, has advanced significantly over the past 20 years. And it's now possible to create lattices which have near arbitrary connectivity between the different lattice sites. This coupling is mediated by transmission lines and is independent of the site separation in the physical space. So what this means is, using some clever tricks, it's possible to implement a variety of lattices, not on our regular day-to-day Euclidean space, but on curved spaces. So this experiment from a few years ago demonstrated the fabrication of a Kagome-like flat-band lattice on a hyperbolic space, which has the following form, which is shown in the middle plot here. So in particular, on the hyperbolic space supports tilings with 5-fold and 7-fold rotational symmetry. And these tilings correspond to generalizations of the Kagome lattice, which similarly have a flat band as their lowest energy band. In contrast to the Kagome lattice on the Euclidean space, however, these hyperbolic lattices have a band gap separating the flat band from the other dispersive bands. So this leads to quite profoundly different properties of the flat band. So I think this ability to emulate exotic spaces, exotic curvatures in the lab is particularly interesting for future theoretical studies of the properties of flat band lattices. Now, second emerging direction is this ongoing boom in quantum technologies and quantum computing. So in particular, we now have access to a wide variety of platforms for performing well-controlled quantum simulation, which allow us to control or to combine strong many-body interactions with the tailored hopping and tailored lattice geometries. For example, recent experiments using the ion trap platform have observed the phenomenon of quantum scarring, in which a complex many-body quantum state is somehow confined to a small subset of the full Fock space. This confinement is due to selection rules analogous to the interference-induced confinement in flat-band lattices. Recent theoretical studies have shown how to understand these quantum scarring dynamics in terms of hopping on peculiar graph structures. And I think it'll be very interesting to apply techniques we've developed for studying flat-band lattices to these kinds of systems. And this paper from PRB last year already started to combine quantum scarring with flat-band lattices. Now, finally, the most natural platform for quantum computing is in gate-based quantum processes. And so these, at their most abstract level, can be considered as evolve a quantum state on some lattice under some controlled unitary operations. Now it's well known that such unitary time evolution is precisely analogous to the time evolution of quantum states in periodically driven lattices. And there do exist examples of flat bands which emerge under periodic driving. However, studies of these Floquet flat bands have remained relatively scarce and mainly limited to the context of topological band effects. I think it'll be very interesting to generalize some of these ideas we have developed in flat band lattices to Floquet systems, which would allow us to make use of these rapidly emerging quantum processes to study the interplay between flat bands and many-body quantum phenomena. Okay, so I'm exactly out of time now. So let me finish with a summary. So I think flat band lattices provide quite a fun and interesting playground for exploring non-perturbative wave phenomena. We have a variety of tricks up our sleeve, which allow us to obtain analytical understanding of these complex systems. Many flat band systems can now be implemented experimentally for light beams, for cold atoms, and for electrons. For example, with the recent observation of electronic flat bands in twisted 2D materials. Finally, I expect in the future, the development of highly controllable quantum processes and quantum simulators will open up new frontiers for flat band physics and hopefully applications. Thank you for your attention. Sorry for the connection issues, and I'll take any questions now.
Thank you, Daniel, for the wonderful talk. I really enjoyed. As an outsider, I mean, a colloquium typically should be targeted to outsider, and as an outsider, I really enjoyed. So it's now time for questions, I think. Okay, maybe I can
ask a question.
Yeah, sure.
Is there anything about flat bands that has to do with the spin degrees of freedom? I don't talk about only stocks.
Yeah,
are
so
people interested in?
Yeah, so I gave this talk from my perspective where I didn't look at spin degrees of freedom, but there are studies of if you add now spinful particles to your lattice, what happens? I think one of these early papers from 2010 or 2011 in the context of cold atoms looked at the properties of you add spin orbit interactions to your lid lattice and you can open a topological band gap while maintaining the flat band. So there are works on this topic. I refer you to these papers.
Thank you.
Okay, maybe I can also ask a question. I mean, you talk about flat bands in hyperbolic spaces, right? I mean, from the theoretical viewpoint, this require new techniques, new ingredients, new tools, or let's say, or it's just another classification problem with the same tools that you developed so far?
I think it requires different tools. I should mention, go back. So this reference on quasicrystals from 1990 is quite interesting because this demonstrated flat band localization on a Penrose lattice. And here the tool which was used was not the band structure because you don't have translational symmetry, only a self-similarity. So here the tool was that to look at the powers of your Hamiltonian operator, and if the nth power of your Hamiltonian vanishes for some finite n, then this allows you to prove that there is a band of strictly localized states forming a flat band. So I think this kind of technique, where you look at the properties of the Hamiltonian operator rather than the band structure itself, could be useful for looking at these hyperbolic lattices.
Okay, yeah.
If you want to see this paper, it's not available anywhere except for Franco Nori's website.
Oh, I see. Okay. Okay. Other questions?
I have questions. So I think that you're talking about the flat band in the work medium, but I'm wondering how is the flat band the system at the boundaries or the domains in between the flat band systems? How is the boundary or domain states is emerged, or what is the shape of this? What can we expect it from?
That's a good question. I specifically didn't mention this because I think it'll be covered in the next talk.
Yeah.
To wait, or can you want me to explain now? I don't know.
Okay, so maybe next speaker, Li Chin Tang, can confirm if she will talk about this or not. Hello?
Hello? You can hear me?
Do you confirm? Yeah.
Hello?
Do you confirm? Yeah. Do you confirm that you will talk about that?
Okay. Okay.
Okay. Okay. We have another question from Tilen. Please, Tilen, unmute yourself.
Yes, thank you, Daniel. Very nice talk. I have a question, kind of follow up on the first paper that you show that didn't get in PRL. So was it experimentally observed then, this Gaussian shape that you've shown?
Yes, it was. The experiment was published in PRL. So that was a happy ending in the end.
Okay, okay, thank you.
Yeah, next question from Sergey.
Yeah, you mentioned the end Floquet physics, and we're calling for more activities from the flatband side. I thought I saw actually some papers or some statements about Floquet flatbands from our friend Alex Summit and maybe others as well. Can you comment on what is actually known in that field?
Yes, well, this is from the Anomalous Summarise paper. So they did realize this Floquet flatband lattice model in experiments. So what they do is that they design this this periodic driving protocol so that the bulk modes during one driving period, they only travel in circles, which is shown in panel B here. So you start at one site, you just hop in a circle like so. This kind of hopping is mediated by coupling neighboring sites in a pairwise manner. So first you couple these two neighbors, then the vertical neighbors, then the other pair of horizontal neighbors, and so on. So since a bulk excitation always returns to its original position after one modulation cycle, this means that the bulk transport is strictly forbidden and the bulk band has to be flat.
Right.
Yeah,
I remember that. But what is then what are you so to say calling for? You said, okay, there is more things which can be done in this area. What, or maybe I missed.
Well, so far our experiments were based on this simple model, which has this flat bulk spectrum. There's no more general theory of how to engineer the driving protocol to create a flat band. Can you create multiple flat bands at different energies? How does this flat band respond to perturbations? Is it the same? Does it behave similarly to flat bands of undriven lattices? Or do you have new effects or new behavior arising due to the Floquet driving?
Okay, thank you.
Okay, next question from Alexei.
Well, this is more of a comment to the question by Sergey. Well, actually, I think there was actually Juzar Tingna at our center. He recently published put a preprint where they discuss how to engineer bands in Floquet systems. And in particular, they designed a rather simple protocol that basically produces a sawtooth lattice as a Floquet Hamiltonian. So there are some advances in that direction. Yeah, I would just like to point out that.
Thank you. Any more questions or comments? Okay, it looks we don't have other questions. So I want to thanks again Daniel for this colloquium. It was really wonderful. So probably it's time to go to the next speaker. We are a little bit on advance on the schedule, but I mean often we are late. So let's use this advance. So let's go with the next speaker, who is Li Chin